All right. Hold up the number of fingers you think would go with the answer for number 1. 1, 2, 3, 4, 0, fist. Is that like a 0?
Fist. 0.
Okay. Okay, it looks like some kind of a code. Total of 3. Total of 3. Okay, so I see a lot of 3s. I saw some 0s or fists. So I didn't look at every single person probably. So is the answer either 3 or this?
Yes.
Those are the only 2 categories I've seen here? Okay, fair enough. So let's hear a defense. People that said 3. What are you thinking? Like, why would 3 be the minimum number of x-intercepts? Hunter?
Because you draw a line from the points, and it turns out to be like something cubic. No.
So,
X to the 4th function.
well, that looks like a cubic-ish looking thing, right? Cubics could look like that. Okay, so Hunter basically saying, hey, I sketched the graph, and look, 1, 2, 3. Okay, so people who said like 0 or fist, defend yourself. Carson, what do you have to say?
There could be like a vertical asymptote where it flips directions.
A vertical, so give me an example of maybe a location for what you're talking about.
Like the far right point and then the one to the left. Like
Okay.
you're going up towards infinity and then it flips and comes from infinity towards the one on the left.
So the far right point, so you're saying like here?
Yeah.
So like that. So you're saying it could do like this and then something like that?
Yeah.
The flipped, you said?
Mm-hmm.
Okay. Whoa, that kind of changes the game a little bit, because could that be true? So if that's true, then that last x-intercept that we had, not there anymore, is it? Okay. So you said your answer was none, possibly, Carson? Okay. So then what would have, because there were 2 more, would we need vertical asymptotes for those 2?
Yeah.
So you're saying maybe like another one right here, perhaps?
No, just in between the last 2. Oh wait, yeah.
I think it would have to be there, wouldn't it?
Mm-hmm.
And there would have to be another one here. So I don't know, maybe it does this and this.
Mm-hmm.
That actually kind of fits the description, doesn't it? Because it goes through all 5 of those points. Yet now there's no x-intercepts. Kind of an interesting question, right? So let me ask you this. I think you could probably say like 0 or maybe kind of a we don't know theme. What's the one element that I did not put in the description that if I did put it in there, the answer would have to be 3? Say again? Yeah, if I told you that g of x was a continuous graph or a continuous function, now all that stuff that I have now, that wouldn't work, would it? Because there's a bunch of points of discontinuity. But if I said that g of x had to be continuous, then we're going to have to go through that x-axis at least 3 times, right? That makes sense? Are you starting to get a gist of this class, how there are some calculations to be done and there's some answers to be arrived at? But there's plenty of this stuff too, right, where it's think and process and discuss and think conceptually, not just I got the right answer and the answer was x equals 10. We do some of that stuff too, for sure. But I kind of like this. I hope you like this stuff too, because we'll keep doing things like this. Any follow-ups before we move on? Okay, so remember, the big takeaway from this is the thing that was brought up at the very end. In order to guarantee that we would be going through, in this case, the x-axis, in order to guarantee that, we needed the function to be continuous. And if it was, then we'd go through the 3 times at least. And if it's not continuous, then maybe it's just 0, right? We just don't know exactly based on not knowing if it's a continuous function or not. So, piggybacking off that, I want you guys to think about number 2. So number 2 says f of x is a polynomial function, and then the table gives some values of f of x there. What is the minimum number of times that f of x equals 2? So again, I want you to do some reasoning here. This is a little bit awkward, right? Because I'm not saying solve this equation. Find theta, right? None of that stuff. I want you to do some thinking. So process, consider, see how you would justify your answer. And I'm curious to see what you have to say. Number of times, just hold up your hand again. Do you think 5?
No.
5
That's not even
times?
an answer.
3 times? 3 times? 3 times? 0, 0, fists and zeros. Does this feel like the first question again? Like a lot of 3s and zeros? Okay, so I would love to hear, I'd love to hear the 3s again, perhaps defend themselves. Like, here's why I think it's 3 times. Anybody want to explain? You let Hunter speak for you last time, and he says 0 now? No, 0? Who's a 3? Somebody had 3 fingers up before?
No one did.
Zach, what do you think?
I was thinking 3 originally because it's a cubic kind of shape, just based on those points.
Did you plot the points out?
Kind of like a rough line. And
Yeah.
to get to all these points, it has to pass through 2 at least 3 times. But I mean, there could be more.
So he said basically a graphical argument, right? He said, so I'm guessing well, you must have done something like, did you maybe, I don't know, here's the y and the x. Did you do, like something like this?
Yeah.
And you said 2 is right here, and so there's 1, 2, 3 times? Okay. Do you see what he's doing there? Does that seem reasonable? Okay. So how about my fists or zeros? Can let Hunter speak for you? Okay, what do you think, Hunter?
There could be holes that asymptote for any number of things.
Okay, so a similar argument to what we had before, right?
Yes.
So it could be some asymptotes, could be jumping right over the 2. Anybody want to have a rebuttal for that? Like maybe some of my 3s say, no, as a matter of fact, that couldn't be true because blah, blah, blah. Anybody have a rebuttal? We had a stalemate here? No one's budging? All right, so basically, doesn't this argument for this come down to basically one concept? Is f of x continuous or not? Because if f of x is not continuous, then Hunter and the rest of his team saying, 0 or fist, they're right, aren't they? But if it is continuous, then the 3s actually would be right. And we can look at some of those details too. So there's one word in here. We actually, the first one was a little bit of a mystery. We didn't ever, we kind of said, we don't really know what's going on with this. In the end, there's really not going to be a mystery with this one. Polynomials have certain characteristics, one of which is they are always continuous for all x values. They are. So here would be, check this out, see if this makes sense. Here would be a good way to communicate this. I would say something like this. I would go f of 2 equals 0, which is less than our target value of 2, right? 0 less than 2. But then the very next point in the table, f of 4 equals 3, and that's bigger than 2. So if we know that f of x is continuous, right there, didn't our graph have to pass through 2 once? And then I keep going, and I say, all right, well, f of 7 is still bigger than 2, but look at that, f of 9, that's 1, and that's less than 2. So because now I've dropped below 2, because of continuity, didn't I have to hit 2 again? And then, as you mentioned, one more time, I guess f of 13 would be that first point we could use. F of 13 equals 7, which is back to being bigger than 2. I pulled that data right out of the table, and there's my third time. So we'd say 3 times, and then you always want to bring this into your argument because f of x is continuous, and we know that because f of x is a polynomial. So I want you to pull those important things out of the description and say, hey, it's important that this is a polynomial because that means this graph is continuous, which means that indeed we did pass through 2 as we jumped around on the table between those values. Okay. Questions, thoughts? Doing okay? All right, so I want to formalize this just a little bit. There we go. So how can we formally state the logic and the reasoning here? What's the condition for using the logic? Drawing a graph, I think, is very, very helpful. So what we've been touching on, and I think you've maybe seen this a little bit in maybe the heading of the section, we've been touching on a concept or an idea called the intermediate value theorem. intermediate value theorem. And we'll often use the letters IVT as an acronym for that. So when you were doing that graph at the start, and when you just worked with that table here just a few minutes ago, the thinking that you were thinking with was intermediate value theorem thinking. You were thinking to yourself, well, if I've got a number above 2 and I've got a number below 2, didn't I have to go through 2 to get there? As long as the function is continuous, right? And so you could think of this in a graphing perspective. I think that's really helpful. So if my target value was 2, just like that last one, what would be something that I'd need to show in order to prove that my graph went through 2? Well, I'd need to find a point whose y value was less than 2, and then another one whose y value is bigger than 2. Yeah. So if I can prove that I've got a point up here somewhere, and I've got another point down there somewhere, if I can prove that, having a table is nice. Graph or a function could work as well. As long as the function I am dealing with is continuous on my interval, then I know that to go from point A to point B, I would have to pass through 2. And if it's not a continuous function, I think you can easily see how you could just jump right over it. And so continuity is the condition. And so anytime you're going to use this IVT thing or this IVT type thinking, you want to make sure that you have confirmed, proven, stated, addressed the continuity issue in one way or another. Does that make sense? Okay. So here is the really formal way of saying it. If f of x is continuous on our interval from a to b, and k is some number between those y values, then there is some number on that interval such that f of x equals k. So can you see why the first thing I did was not to just like throw this formal IVT at you? It's sort of like, whoa, what? What are you talking about? Isn't it so much easier to look at it from a graphing perspective or a table perspective? And I'm not really interested in you rewriting the definition of the IVT. I'm really interested in you understanding the logic behind it. Continuity is the condition. I got to basically bracket my target number. And if I can do that, then the IVT guarantees that I'll hit the target number. Is that okay? What's the condition for the IVT? It's the big takeaway here, okay? So we're going to finish up with our one last example, and it's on the next page, so if you would, check that out. It's over here. Okay, so this is a nice tie-in to some other stuff we've been doing. It says, if f of x equals that piecewise function, use the intermediate value theorem to show that f of x equals 5.217. For some reason we care about that number. At least once on the interval from -3 to 3, and remember to confirm that the IVT's condition has been met before you actually use the IVT. And what's the one condition for the IVT? Continuity. So you better confirm continuity before you do anything else. And if I'm asking you to investigate continuity, what should you use? Limits. Yay. We're doing good. We're doing good. Okay, so confirm continuity and consider, if it actually is continuous, consider what to do. Bless you. Okay, so I want to show you what I wrote here. All I've done here is I've dealt with the continuity. You guys all have this? Okay, so if you have that, we can say, therefore, f of x is continuous on the interval -3 to 3. Now that we have shown that we have a continuous graph, now you can try to use the IVT, right? The condition for this to make any sense has been met. Yes, ma'am.
Is that an M before the?
Oh, it's an on.
Oh, okay.
Sorry. I think
No,
you guys
I'm
will
sorry.
find that I have many strengths and weaknesses. One of my weaknesses would be really nice writing. So please don't feel bad if you have to ask a question like, what exactly is that letter up there? I'm not going to be upset. Thanks for asking. Okay, so we have a nice continuous graph. What do we need to show in order to use the IVT? What's our target number? Like, what are we trying to prove that this actually goes? So if you're trying to prove that f of x equals 5.217,
Then you just plug in some number that gets there.
Would you plug in like
Well, but-
-3 for the lower half of the piece five and 3 for the top half?
maybe. What are we looking for on the outputs? I mean, we're talking about plug this in, plug that in. I mean, Carson's saying, let's just magically figure out how to plug in something and get out a 5.217. I don't know how to do that. I don't think you do either. So if we started by plugging in the -3 and the 3, what would we hope to find?
One number
Then -3 is
One below and one above. There you go. So you could use your calculator here and try to figure out the one below, one above. I don't think you need to. I think you could maybe take Cole's idea with the +3, -3. Huh.
So after we have that, do we have to?
Relate those to the 5.217. This is less than 5.217. This is bigger than, right? So if you've shown that you have a continuous graph and you have a value above your target and a value below your target, what did you have to do?
Go through.
You had to go through the
So
target,
that's
right?
all we need.
So that I would just say, based on all this good work that you have, and that you can now make your conclusion and say, yes,
Yes, it goes through.
we have shown it using the IVT. We've proven it. QED, if you will, right?
I did -3 and -2.
Well, you can just find
So that proves.
That works too, yeah. Yeah, I think this is one you should be able to do without a calculator as long as you pick like strategically smart numbers.
Right.
But I think you did. I think you did do that. Yes, sir.
How would you conclude, because I proved that was continuous, and then
You know what? I'll show everybody.
Okay.
That's a good question. It'll be a pretty easy tie-in, but you do want to conclude. You ask a good
Yeah.
question, for sure.
No, that part, sure.
Yeah. Okay, so let's tie this one up and wrap it up here for the week. We proved continuity, and hopefully, I'm hoping you're getting really good at that. This is our third day in a row, essentially, of talking about continuity. Hopefully, that's going well for you. But then, how do you use the IVT? I want to try to make it as simplistic. I mean, it's kind of a hard concept, but I want to try to make it as simplistic as I can. If you can find a y value on our interval that's below and another one that's above, haven't we essentially gotten where we need to go? So I'm thinking I would do this just as a try it out sort of an idea. I'm going to try out f of -3. F of -3 would be the parabola. It would be 7. Now, how does 7 relate to my target value?
It's greater than.
Bigger, yep. So I'd say bigger than 5.217. And then I'd just try the other endpoint, not because there's anything special about endpoints. I'm just going to try those out and see what happens. F of 3 would be cosine of 3 pi. And what's cosine of 3 pi? -1. And how does that relate to my target? Yay! So I just found a number below and a number above. Or above and below, I guess, the correct order here. And so all I really need to do is think, did I prove continuity? Yup. Did I find a number above and a number below? Yup. So all I have to do now is just say, therefore, you could say like, because of the IVT, f of x must equal 5.217 at least once, at least one time on my interval, -3 to 3. That make sense? So just tie it back to what was asked in the beginning. But if you proved continuity or confirmed continuity and you got your target value, they basically bracketed your target value, now you've like got all the elements there. You just need to say, I proved it, and here it is. What do y'all think? Okay? Okay. So I have like 50 seconds left, and I'm gonna mostly use them here. So I want to show you one thing here. We have kind of a unique thing coming up for our first meeting next time, I think. I think I'm right. Okay, so we finished concept 2. That was the end of continuity in the IBT. So if you move on to Unit 1, Day 6. Yep, I figured this was it. So if you look at Unit 1, Day 6, and this is listed in your Schoology, this is called Intro Activity 1, and it's you watching a YouTube video, recording a few things, looking at a few little minor calculations. You might want to have your phone with you because, or some kind of a timing device, although I can't remember how it works out on YouTube as far as timing. But you can see you're going to be watching this John Ross guy, I think I mentioned him earlier, running the 40-yard dash. And I'm going to, you can see some of the questions here asking you about his average velocity in certain areas. So there's some pretty hilarious videos of 40-yard dash times and things, and this guy is one of the fastest ever. I think he might be the fastest ever to this point. One thing I wanted to bring out to you, something I planned on doing, but I'm not going to do. Please notice down here on the next page it says, use the class discussion on Schoology to consider your answers to the intro activity. I'm not going to have you do that. I'm just going to have you come to class having completed that intro activity, and then we're going to piggyback right off that into what we're going to do. I don't want the intro activity to take you that long. Like if you put all the technology away except for the computer, like it should be like 10 minutes or less. Just a quick kind of student out, see how fast he ran, what was his average velocity, figure out what average velocity even is, that kind of thing. Then come to class and be ready. Make sense? All right, have a great day. See you guys.